Hello again. This is Math 2 333 coming to you from the College of DuPage, and the title of this lecture is Vectors, Direction Cosines, Scalar Projections, and Work. And as always, I encourage you to be an active learner as you watch this video. In the same way that we could use unit vectors I, j, and k to represent a vector, we can talk about the angles that a given vector A makes with each of the coordinate axes. These are called the direction angles of a non-zero vector, are the angles alpha, beta, and gamma on the interval from 0 to pi that vector A makes with the positive x and y axis respectively. And here is a picture. The cosines of these direction angles, cosine alpha, cosine beta, and cosine gamma, are called the direction cosines of vector A. And if we use our formula that we just had about finding the cosine between these angles, or between vectors, we can say what is the cosine of the angle between vector I and the vector A. We can use this formula and conclude that the cosine of alpha is a1 over the norm of A. And you can see that directly from the picture as well. And similarly, cosine of beta is a2 over norm of A, and the cosine of gamma is a3 over the norm of A. Now, if you square those and add them together, clearly you will get 1. And so that means that the length of this vector here, cosine alpha, cosine beta, cosine gamma, is 1. And any vector A then can be found by taking A times each of those unit vectors. And so you see we have decoupled A into the magnitude of A and the direction of A. This is often useful, and this is summarizing that, just writing it in a little bit different way, that A over the norm of A is the direction cosines as a vector, and that means this is telling you the direction that vector A is pointing. So let's apply this. Find the direction angles of the vector, capital A equal, pointy bracket, 1, 2, 3, into pointy bracket. You know what to do. Let's see how you did. Okay, this is the magnitude of A is the square root of 14, and it was 1, 2, and 3. So it's a pretty easy calculation. And if you wanted to know what the angles were, you would take the arc cosine of each of these, and you would end up with these as approximate angles. In many applications, it is useful to take a vector B and resolve it into perpendicular components, but the components are not necessarily directed along a coordinate axis. They can be in any direction, shown as PQ here. This gives rise to the idea of projections. So in figure 4, this shows the representations of PQ and PR. Here is PQ and here is PR. Of two vectors A and B with the same initial point P. So if S is the base of the perpendicular, or the foot of the perpendicular from R to the line containing PQ, then the vector with representation PS, this shorter one, is called the vector projection of B onto A, and is denoted by projection, and that you say B onto A. And you can think of this as the shadow of B, and we have this picture, and you note that this also could be in the opposite direction of A if it turns out that the angle between the two vectors is obtuse. Now, the scalar projection of B onto A, also called the component of B along A, is defined to be the signed magnitude of the vector projection, which is the number, and we're using this formula again and again and again, norm of B times cosine of theta, where theta is the angle between A and B. And so we have this formula for norm of B times cosine of theta. We get this expression, and that is going to be the scalar projection. And we'll summarize that with the following picture, and you can see if we took norms everywhere, this would be easy to get. So that is what this projection of B onto A. That's the scalar projection. That's the component there. Now you should notice that B is the orthogonal sum of this vector and this vector, so they add up to B vector B. So the scalar projection of B onto A is a scalar, and it's this B dot A all over the magnitude of A, and the vector projection is that number times the unit vector in the direction of vector A. And so this is a formula for the projection there. And so you see it's easy then to decompose a vector B into perpendicular components that add up to that, and this can be taken in any given direction, or in the direction of A rather. Okay, so notice that the vector projection is the scalar projection times the unit vector in the direction of A. I guess I already said that. Okay, so let's do this as an exercise. Find the scalar projection and the vector projection of this specific B, pointy bracket, 1, 2, 1, 1, 2, and A equal pointy bracket, minus 2, 3, and 1. You know what to do. Let's see how you did. So we calculate this to be the square root of 14, and then I use the formula, and so this is the scalar projection of B onto A, and the projection then, the vector projection of B onto A then is this times the unit vector in the A direction, and you get this as your answer. Now, one use of projection occurs in physics in calculating work. And remember, we defined work done by a constant force in moving an object through a distance w as F times d. But this applies only when the force is directed along the line of motion of the object. Suppose, however, that the constant force is a vector, F, operating from P to R, pointing in some other direction. And here, for example, you could think about you're pulling a wagon or something. You have the tongue of the wagon up here, so you're pulling in a direction. So you see the only direction that really matters is this one, and you see the projection is starting to loom large here. Okay, then the displacement vector D is PQ, where Q is along here. That's the direction of the displacement. So the work done by this force is defined to be the product of the component along D, which is going to be the projection. That's the magnitude of F times cosine of theta times the magnitude of D. So that is the work. There's the picture, and so that means that W is equal to the product of these two things. We already showed that, but that's equal to F dotted with D. So the work done by a constant force is the dot product F dot D, where D is the displacement vector. So suppose a wagon is pulled a distance of 100 meters along a horizontal path by a constant force of 70 newtons. The handle of the wagon, or the tongue of the wagon, is held at an angle of 35 degrees above the horizontal. Find the work done by the force. You know what to do. Let's see how you did. We just use the formula. It's F dot D. We have this, and that's approximately this many joules. And there's a picture of what's happening with the wagon. It doesn't have to be horizontal. However, we could say a force is given by a vector F in this direction and moves a particle from this point to this point. Find the work done. I didn't put the graph here, but you know what to do. Let's see how you did. So it is F dot D, but first we have to figure out what is the vector PQ, and so it's going from here to here, so we compute that this way, and then the work done is F dot D, and we get 36, and this has to be joules. In closing, Now, more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. God bless you all.